Hello everyone. Today I would like to share an idea about plan model generator from digital twin for purpose of formal verification. Let's start with a brief introduction. Formal verification of automation system is a promising technique to automatically verify the correctness and safety of the automation system. Previously, formal model of the plant is constructed manually, but it would be great if it was possible to build the formal models automatically. So how to generate a plan model automatically? Process mining can be used to extract the process from event log. That is, it is possible to extract the logic of plan with the help of trace file. Nowadays, simulation models are widely used for manufacturing system. They are popular for purpose of illustration, virtual commissioning, maintenance, etc. The simulation model doesn't ensure 100% verification and validation automation system, but we can record the event with the help of simulation models. This paper explores an approach to automatically generate a plan model of control system from traces of digital twin and ensures that the generated formal model consists of desired plan behavior. Now let's see a case study and how it can be done. The energy autarkic actuators and sensors in as a testbed located at Aalto University representing a small-scale industrial production scenario and is used for development and testing of various industrial automation techniques. It included with a set of pneumatic operators such as jacks and grippers, motor-driven conveyors, and laser sensors. An accurate simulation model of INAS has been developed using Visual Components 3D simulation environment. In this research, the simulation model was connected in the loop with the automation controllers. The figure shows the visual representation of a digital twin. The major components are the main plant, the automated guided vehicle AGV, and the isolated IRB subsystem. The following part briefly explains the major software applications used. The controller of the plant is created using NxtSTUDIO and the controller is connected to the plant in visual components via OPC-UA communication protocol so that the controller can receive the status updates from the plant as well as it can control the plant through the various signals. Proposed solution. The solution was as follows in the figure. The digital twin communicates with the controller which is designed in IEC 64099 standard with the help of an ST control software. The function block representation of controller in SMV file is then fed to FP2SMV tool, which generates SMV code for controller and also provides skeleton structure for the plan model to incorporate closed loop verification of the whole system. The digital twin application records the behavior of the plan and the output from the application is added to a trace file. The trace file consists of a raw text describing the behavior of the plan. The model generator creates a model file depending on the order of the recorded actions in the trace file. Formal model of the plan is then added to SMV skeleton structure provided by the FP2SMV tool. The functional properties and safety properties of the systems are added to a model file prior to model checking. The updated model is fed to a symbolic model checker tool, NuSMV, which verifies CTL LTL specifications of the system. The NuSMV determines whether the specifications are true or return the counterexample which show where and how our properties do not hold true. Closed loop verification of plan model from digital twin. The process to reach the goal is split into following parts. The first one, trace generation from digital twin. In visual components, whenever an action occurs, it records the event into a trace file. Each event contains timestamp, subsystem, component, and action. The second one, model generation from event log. The basic SMV code structure of the plan model is created with the help of model generator algorithm. The model generator sorts the trace according to the ascending order of the timestamp, declares and initializes the each component's variables, and finally transitions of each variable is identified by analyzing each entry in the trace. The next one, embedding the plan model into SMV code structure provided by FP2SMV tool. The following challenges are occurred while combining the plan model into SMV code. Receiving the control signals from the controller to the plant, insert the logic of plan model, passing the sensor value to the controller. And finally, updated SMV code is given for verification purpose. Conclusion and future plan. We implemented the SMV model of the conveyor subsystem and connected to the controller for closed loop verification. Testing and validation is done with the help of NuSMV by checking various properties of the system. The analysis of the solution yields a promising result. The model generator is consistent in generating a formal model of the plan because the specifications of the formal model provides the expected output for more than one trace. To improve the legitimacy of the solution, it should be applied to another system to see if it works well. The implementation of a tool which automates analysis and verification of system properties requires an extensive development process. However, it is possible to come along with the automatic generation with minor additions to finalize the process. And another point of future work that was not explored at all but might be an area of interest is simultaneous running of analysis alongside the actual plant. In this approach, we need to generate a model during runtime instead of generating model using traces from a specified time. The benefits of approach makes the system analysis in real time instead of after the fact. We need to make sure that the digital twin records all possible traces in the plant, otherwise the verification process may fail. Ensuring the digital twin contains all problematic traits that are possible in the plant could be next step in future. Thank you for listening to this presentation.